As we have seen in the video before, the degree reasoning is not enough for the all different constraints. We need to do something more to prevent the closing the subtours before having only one subtour in the final circuit constraint, and we are not allowed to have subtours. So we will introduce here a very efficient filtering that prevents closing too early the circuits. It's called partial path reasoning. So the idea is that we will maintain and we will define as partial path, we will maintain them. A partial path is a maximal successive sequence of nodes with a unique successor. Okay, so with a unique successor, it means that these variables are fixed, okay, and we know the direct successors of each of these variables. So let's see what are the partial paths on this graph, according to our definition. So we have, for instance, starting from 0, we have here in red, we have one partial path that is represented here. And then at the node number 6, we see that we have more than one possibilities, and so the partial path is stopping there. But we have also a partial path starting from node 8, okay, until node 14, and then we have at least two possibilities, so we stop there. And we finally have, in this example, a partial path that is represented here. Okay. The general idea of the filtering that we'll use is that if the partial path that we have detected is too short, then we will prevent this partial path to be closed. And so too short means that if the partial path has fewer than n-1 edges, where n is the number of nodes here in your circuit constraints, then it must not be closed. Otherwise, we would have a subcircuit. And so we can remove the edges, this one, these ones, and this one, since if you would assign the successor of 6 to 0, you would close here the subcircuit. And that's not allowed. We don't want to have a subcircuit that is closed. We want to have only one circuit. That's the same here, and it's also the same here. We want to prevent closing the circuit here. So let's continue our example, and we will further assume here, we will also see here that because we have removed this edge, we see that here 14 has only one single successor, which is 12. Because of the all different filtering that is also doing his job, no other cities can have 12 as a successor. It means that the 4, this edge, should also be removed, because otherwise we would have 2 times the same successor for 2 different cities, and that's not allowed. So we will remove this edge as well by the reasoning of the all different constraint. And actually that's the forward checking reasoning here on the all different constraint that will be able to detect that one. So in terms of data structure, to store the partial path and do efficiently the partial path filtering, we will store 3 pieces of information for every node in the graph. We will first remember the destination node of the partial path starting from the node I. And so initially the destination of node I is I itself if the successor of I is not fixed. We assume that it's a loop. And then we will also store for each partial path the origin of the partial path for each node. Okay? And then finally we have the length to the destination of the partial path, the length to the destination of the partial path. So let's consider one example to make sure that we are on the same page according to the values that I just have introduced there. So what is the destination of node 6 here? The destination of node 6, since the partial path is ending in 6, it's 6 itself. And the origin of the partial path ending in node 6, you see that it was originating at 0. That's this one. The length to the destination of the origin of 6, so the length to the destination of 0 is 4, because we have 1, 2, 3, 4 edges. Let's consider 2 more examples. So we are interested to the destination of the node 8. And so the partial path destination of node 8, you see that it's ending in 12. Okay, this is why we put 12 there. The origin of the partial path ending in 12, we come back here on the partial path, you see that it's 8. And the length to the destination here of 8 is 1, 2, 3, 4. Again, we have 4 edges until the final destination of the partial path originating in 8. If we consider 0, this partial path, the length to the destination of the partial path at node 0 is 6, because we have 6 as the destination of this partial path. The origin of 3 here, the origin of that one, you see that it's 0. Okay, so the introduction of these variables is also valid in between, so in the middle of a partial path, you see that the origin of 3 is 0. The length to the destination of node 3 is only 2, because we need 2 more edges, to visit 2 more edges to reach the end of the partial path going through node 3. These three values for each node can be maintained incrementally and can be updated in constant time. And that's really the strength of this reasoning. So assume that we have taken a branching decision, and we have taken that according to the search. After visiting the node 6, we should visit the node 8 in the circuit. So the successor of 6, all of a sudden, by the branching decision, becomes 8. What are the consequences of that? How can we update the partial path information, that the length to the destination and the origin nodes? Well, what we can see is that the destination of the origin of 6, okay, is now 12. So we take the origin of 6 that we have already available, that we have computed before, so that's 0, and we set the origin of 0, we set the destination of 0 as the destination of 8. And we can do that in constant time. And so now we will have that the destination of 0 is pointing to 12. Okay, this is what we do. But the origin here, the origin of the destination of 8, so the origin of 12, can also be set to 0. Here. So the origin of the 12 can also be set to 0. And in terms of the length to the destination, we can also update that in constant time. The length to the destination from 0 is equal to the length to the destination that we had before. So it was 1, 2, 3, 4, plus the length of this partial path, plus 1. Okay, and so we will have here the length to the destination from 0 is equal 9, because it was 4 plus this new edge that we have just detected, that was created in the partial path. Okay. And once we have that, we have a longer partial path now. Okay, we have created this partial path. And we should prevent it from closing too early, because the length of that one is less than n-1. And so we need to remove this edge. This edge should be removed, should be pruned. Okay, and so as a consequence, we see that the successor of 12 cannot be 0. That will be one pruning that will be detected by the partial path written. Okay, and since that one is pruned now, we see that this new edge is fixed. And because this new edge is fixed, we will again update everything. We will again update the origin, the destination of node 0, okay, because we know we have continued a little bit the partial path here. And so this partial path should also be prevented from closing too early. Okay, and so in that case, you see that what will happen is that we have actually fixed the circuit. We have assigned all the variables just by using the partial path reasoning on this example. So that's quite powerful, the kind of deduction that it can make. And the pseudocode to do that, I give it here, is this one. So initially, we have the destination of each city is the city itself. The origin of each city is the city itself as well. And the length to the destination of the partial path going through I is set to 0. And then we will loop over all the variables. And if we detect that one variable is fixed, for instance, the successor of I is detected to be equal to j, then we need to update the partial path. So we detect here that one variable is fixed, and so the successor of the variable I is fixed to some value, and without loss of generality, let's call it j here in the loop. Then we can update the destination of the origin of I, so the origin here of that one, the destination of this node now will become that one, and the origin of that one will become that one. And in terms of length to the destination from that one, we say that it was this length plus 1. This is exactly what we are computing there. And you see that these updates can be performed in constant time for every edge that is detected as newly fixed. And if the length to the destination here is less than n-1, we prevent to close this subtour. We prevent it by removing the value. We remove from the destination there. We remove from the successor of that variable. We remove the origin I. We remove that value. Okay, and so that's the complete filtering algorithm that you can do to implement the partial path reasoning for the circuit constraint. Can we make this implementation more efficient? Actually, yes, it's the case, and we should do some incremental reasoning there. And we can really update these three types of values incrementally during the search in order to avoid to have to loop over all the variables there. And so we can trigger this code only when xi is fixed, okay? And so we can attach a triggering event to the detection of xi that is fixed. And if we realize that a new variable is fixed, and you can also do that, for instance, by splitting the set of variables between using a sparse set, using the fixed and the not fixed variables, if you detect that the new one is fixed, and so in that case, you don't need to loop over all the n variables, but only on the ones that are not yet detected as fixed, and then you do this update here in constant time. So you can have a total time complexity of this filtering algorithm that is proportional to the number of newly fixed variables. So that's very efficient.